All right, good morning, everybody. So let's continue with the lectures. So let's do the share screen, share the PowerPoint. Okay, so remember that what we are seeing now is all the possible reactions that may happen in a catalytic cycle during a catalysis reaction. So on Monday, we covered the first part, reactions involving gain or loss of ligands. I showed you ligand dissociation and substitution, oxidative addition, reductive elimination, and nucleophilic displacement. The goal for today is to cover the second part, or starting covering that. It's quite long. So now we are going to take a look at reactions involving modification of ligands. In other words, we are going to do reactions that change the structure or the formula of the ligands that are coordinated to the metal center. 4 different types: insertion, carbonyl insertion, that's also named all-alkyl migration. We also can have hydrogen migration or hydride elimination and abstraction. Today I will cover insertion and alkyl migration. Okay, so let's start with insertion. Pretty simple. The molecule is inserted in between an existing metal ligand bond. There are 2 different types of insertion, 1,1 and 1,2 insertion. Let's start with the 1,1 insertion. So we are going to show here, I'm showing here an example of a manganese complex, hexa-coordinated. We have 1, 2, 3, 4, 5 carbonyl ligands and 1 methyl ligand. We are going to react this complex with sulfur dioxide. And if it's an insertion reaction, this compound is going to be inserted in between manganese and methyl. So the product, we still have manganese with coordination number 6. However, now we changed the structure of the ligand. Now we don't have methyl, just methyl anymore. We have a sulfoxide group here bonded to the methyl, okay? So manganese and CH3 are bonded to sulfur, or the same atom. Therefore, this is a 1,1 insertion reaction. Now let's take a look at the 1,2 insertion. Starting with a cobalt complex, the insertion is going to be made in between cobalt and hydrogen. And here we have the ethylene, okay? So we have here atom number 1 and atom number 2. This whole compound is going to be inserted in between cobalt and hydride. Now the carbon number 1 is bonded to cobalt and the carbon number 2 is bonded to hydrogen. So can you see that cobalt and hydrogen are bonded now to different atoms? Therefore, this is defined as 1,2 insertion. Okay, moving on to carbonyl insertion, or also called alkyl migration. Insertion of a carbonyl ligand, or CO, that's what's going to be covered here, looks like a very simple reaction, but the mechanism is quite complex. Okay, so the overall equation is very simple, looks very simple. So we are going to insert the carbonyl in between manganese and CH3. So that's what's going to be formed. So CH3COO, that's called acyl group or acyl group. And that's what's going to be formed in this reaction. There are three different proposals for this reactions mechanism. So let's take a look at each of those proposals. So proposal number 1 says that there is direct insertion of the CO ligand. Okay, very simple reaction, CO being directly inserted here, forming the acyl group and changing the structure of the methyl ligand. Second proposal, or also called CO migration proposal, states that first there is a migration of a CO ligand and then addition of CO to the coordination sphere. So in this proposal, the first complex here, the CO ligand migrates over here, producing the acyl group, the COCH3, and as a consequence, there is a vacant site here in a 5-coordinate intermediate. Then a CO2 reacts with this intermediate and forms a hexacoordinate complex. The proposal number 3, or also called alkyl migration, states that first there is CH3 migration and then addition of CO to the coordination sphere. Okay, so starting again with the hexacoordinate complex, the alkyl group is the one that migrates over here. So that's going to form the CH3COO that creates the vacant site here and a 5-coordinate species as the intermediate, and then the CO bonds to the vacant site, reestablishing the hexacoordinate complex. Okay, so careful. Proposal number 1, straight insertion of CO2. Proposal number 2, the CO migrates, and then there is addition of CO to fill up the coordination sphere. Proposal number 3 states that the alkyl group is the one that migrates, creating a vacant site here that's going to be filled by the CO2 ligand, reestablishing the hexacoordinate species. Okay, so you have to understand the difference between the 3 proposals. So now the next step is to analyze each of the proposals with experimental data and see which one is the most correct or the most accepted. Okay, so let's do the experiment number 1, which is a simple reaction using carbon monoxide labeled with the carbon-13 isotope. So I'm going to represent this carbon monoxide labeled with carbon-13 as a red carbon bonded to a regular oxygen. Okay. According to the proposal number 1, there is direct insertion of the CO ligand. Therefore, all the carbon-13 will be transferred to the acyl group, and we will find all of the carbon-13 here in the acyl group. However, the result shows that there is no carbon-13 in the acyl group. Therefore, that rules out the proposal number 1. Okay, no carbon-13 found in the acyl group. Okay, second experiment. So now we have to test proposal number 2 and proposal number 3. For the second experiment, we are going to investigate the reaction in the opposite direction using carbon-13 labeled in the acyl group. Okay, so now we have here carbon-13 in this group over here. And the reaction that we are looking is this one. Okay, so now we are going to lose a carbon monoxide molecule and reestablish the starting complex with 5 CO ligands and 1 methyl ligand. So let's test first proposal number 2, which states that there is CO migration and then addition of carbon monoxide. Okay, according to this proposal, all the CO that this group has is going to migrate to the vacant site, and that will reestablish the starting complex. Okay, so there is a loss of carbon monoxide and migration of the CO group from the acyl group, and that reestablishes the starting complex. So let's take a better look at this reaction. So this is the experiment. This is what proposal number 2 states. Here is a very generic reaction for this mechanism. And let's analyze all the possibilities that can happen in this kind of reaction. Okay, so as you can see here, this carbon is in red. That means it's carbon-13, and it's the labeled carbon for this reaction. The first step of this reaction is loss of one of the CO ligands. We have here 1, 2, 3, and 4 possibilities of losing the CO ligand. You may consider a 5th possibility right over here. However, this is very improbable to happen, low probability, because there would need to be a migration to a very far position, which is very unlikely. Okay, so therefore we are going to just consider the migrations to the um, positions right next to the acyl group. So the first possibility is losing the carbonyl group at the top of the structure. So that's what's going to happen. So losing this ligand in this position, and then migration of the CO from the acyl group, and all the labeled CO is going to be in a cis position relative to the methyl group. The second possibility is to lose this carbon monoxide, this CO ligand over here, then migration of the labeled CO to that position, and that generates labeled CO cis to the methyl group as well. Now we can lose the CO ligand at the bottom of the structure, creating a vacant site here, migration of the CO to that position that produces a complex where the labeled carbon monoxide is also cis to the methyl group. And the fourth possibility, lose this carbon monoxide over here, creating a vacant site in that position, migration of the CO to that empty site, producing a complex where all the labeled CO is cis to the methyl group. Okay, so according to this mechanism, all the four products have carbon monoxide and methyl ligands cis to each other. Okay, now I would like to take a look at proposal number 3 to see if the results will be different from proposal number 2, and then we can make a decision which proposal is the most correct, or which one is the one that explains the experimental data. Okay, so we are going to do the same experiment, but now we are going to predict the products using proposal number 3, which means there is alkyl migration. Okay, there is alkyl migration, and that's the difference between number 2 and number 3. Okay, for number 3, the CH3 group is the one that moves, not the CO group. And remember that we are analyzing the reaction in the opposite direction. So first, lose one of the CO ligands is lost, creating a vacant site that the methyl ligand, the methyl part of the ligand will migrate and produces the hexacoordinate complex. Remember that we are using labeled carbon in that position. Okay, so again here I'm showing the labeled carbon in red. So now let's do the same thing. Let's analyze all the four possibilities. Remember that the fifth possibility is unlikely to happen because that would require migration all the way to the opposite side, which is unlikely. And I'm going to do the same thing as I did before. So let's start losing the carbon monoxide in the top position. So that will create a vacant site right over here that the methyl ligand will migrate, and that will produce a complex where CH3 and labeled CO are cis to each other. What about if we lose this carbon monoxide over here, creating a vacant site in that position, migration of the CH3 to that position that produces a manganese complex where labeled CO and CH3 are again cis to each other. Third option, losing the carbon monoxide at the bottom of the structure, creating a vacant site right over here, migration of the CH3 will result in a hexacoordinate complex where CH3 and labeled carbon monoxide are again cis to each other. And the fourth possibility is to lose the carbon monoxide in this position over here, creating a vacant site in that position. The CH3 will migrate over there, and that will produce again a hexacoordinate complex where CH3 and carbon monoxide are cis to each other. Therefore, according to proposal number 3, all the four complexes, all the four products have the labeled carbon monoxide and methyl ligands cis to each other, which is exactly the same conclusion that we got with proposal number 2. The result of this experiment is that all the products formed have the CO and CH3 ligands cis to each other. Therefore, that does not rule out proposals number 2 or number 3. Okay, so with this experiment, we were not able to differentiate the two proposals. They gave the same result, which is what was observed, so we cannot rule out any of the proposals. So we need an extra experiment that will differentiate the two proposals, and then we can decide which one is the most correct. Okay, so let's do a third experiment, and hopefully this one will be able to differentiate both proposals, and then we can decide which one is the correct. So now what we are going to do is to investigate again the reaction in the opposite direction using labeled carbon monoxide cis to the COCH3 group. Okay, so now we are going to label this ligand with carbon 13. It is cis to the acyl group, and let's take a look at proposal number 2 and proposal number 3 and see what are the products predicted by each of the proposals. Okay, remember that proposal number 2 states that there is CO migration to the vacant site and the CH3 stays over here. So let's do the same thing that we did before. Let's test all the 4 possibilities and see what are the products formed. Okay, so first possibility is to first lose the CO at the top. That will result in migration of the CO group to the vacant site, producing CO cis to CH3, but no carbon 13 in the structure. Okay. Second proposal, lost. This ligand is going to be lost. Migration of the CO group to the vacant site will result in the hexa coordinate complex, where labeled CO is cis to the methyl group. Third option, losing the CO at the bottom, migration of the CO group to that position, resulting in this complex shown over here, where again, the labeled carbon monoxide is cis to the methyl group. And the last option, losing the ligand in that position, creating a vacant site over here that followed by migration of the carbonyl group over there, and that produces again the hexa coordinate complex with the labeled CO cis to the CH3 group. Therefore, according to proposal number 3, one product does not have CO 13 or labeled carbon monoxide, and the others all have labeled carbon monoxide and CH3 ligands cis to each other. Okay, attention to that. All the 3 products formed that have labeled CO, it is cis to the CH3 group. Okay. Now let's investigate with the proposal number 3 predicts for the products of this reaction. Remember, proposal number 3 states that there is migration of the alkyl group. okay? Migration of the alkyl group. So we are going to do exactly the same thing. The labeled carbon monoxide ligand or carbonyl ligand is at the top position. The first step is loss of the carbonyl ligand. So first possibility is to lose the top ligand. Migration of the CH3 to the vacant site will result in the hexacoordinate complex. And in this case, there is no carbon 13 or labeled carbon in the structure. Okay. Second possibility, this carbonyl ligand is lost. The CH3 group migrates to the vacant site, producing a hexacoordinate complex where labeled CO is cis to the CH3 group. Now let's take a look at the third option. If we lose this carbonyl ligand, now the CH3 is going to migrate to this vacant site right over here. And now take a look at that. Now what we got is the hexacoordinate complex where the carbon monoxide labeled with carbon 13 is trans to the CH3 group. Fourth possibility, this carbonyl ligand is lost. Migration of the CH3 group to the vacant site right over here. That will produce a hexacoordinate complex where labeled carbon monoxide is cis to the CH3 group. Okay, so now let's take a look at all the products predicted by the proposal number 3. First one has no labeled carbon monoxide in the structure. Second one has labeled carbon monoxide cis to the CH3 group, as well the fourth. But the third one has labeled carbon monoxide trans to the CH3 group. Okay, now we have a difference between proposal number 2 and proposal number 3. Proposal number 2 produced one product without CO, 13, without labeled CO, and 3 cis products. However, proposal number 3 produced 2 cis products, 1 trans product, and 1 product without the labeled CO as well. Now we have 2 different results using proposal number 2 and proposal number 3. So now we have means to define which proposal is the most correct. So let's see what is the result of the experiment. So the result says that there is indeed a 2-to-1 cis-trans mixture of products formed. Therefore, the proposal number 3 is the correct. And proposal number 3 states that there is alkyl migration. Okay, so first the CH3 migrates, and then there is addition of the CO ligand in the vacant site. Okay, so all the carbonyl insertions, the mechanism is through alkyl migration. Okay, therefore the name carbonyl insertion is a little bit misleading, because actually there is alkyl migration and then insertion of addition of a carbonyl ligand in a vacant site. Okay, and that's the correct mechanism. And take a look at this reaction, see what we can do. We started here with CH3 and ended up with CH3COO. So we changed first the size of the carbon chain, and second, we added a functional group that did not exist before. Okay, so catalysis is very important in organic chemistry. So with catalysis, we can increase the length of carbon chains, we can change the saturation of the chain, and also we can add organic functions that were not there before. So I think that's a good point to stop. So Friday we will have the in-class assignment. Then next week on Monday, I will show a little bit more about the alkyl migration mechanism. I will also show you hydrogen migration, and then we will cover the 2 other topics for this type of reactions, okay? So let me know if you have any questions, and I will be happy to answer any of your questions, okay? Have a good day.